Hello everyone, welcome to IIT classes. Today we will be going through the communication system problem that were asked in Electronics and Communication Gate 2021 paper. So first let's go to how many questions that were asked. So in 2021 Electronics and Communication paper there were total 11 questions based on the communication system, and out of the 11 questions 6 of them were 1 marks and 5 of them were 2 marks question. So in total it carried total 16 marks. Now let's go through them one by one. Okay. So the first problem is based on the random process and the random variable. So in this problem, two random variable x and y is given and their relationship is given. So y is equals to 2x plus 3, and we need to find out the how the variance of the x and y are related to each other. So here we will use a property that if you have any uh, random variable y and x which are related as, or let me generalize it, y equal to ax plus b. So let's say there are two random variable x and y which are related by this, and a and b are constant. Okay, in that case the variation of y and x are related as, okay, so this is the relationship, this will be the relationship between the variance of x and y if this is the relationship between y and x. It doesn't depend on the b. So if you compare this with this, here a is equals to 2. So the variance of y will be 4 into variance of x. So this will be the correct option. So if you know this property and the formula, we can easily calculate what will be the relationship of the variance of x and y. Now let's go to the next problem. Okay, here we have a signal xt, and it's a band limited signal, and it's band limited to 10 kilohertz. We need to find out the Nyquist of the new signal yt, which is xt into x1 plus t by 2. So in this problem there are a lot of property we have to use, and all of them comes from the Fourier transform. So first thing is that if you have any signal xt, and let's say its bandwidth is a, okay, and let's say you have a new signal xt by 2. So here you're doing the time scaling. If you do the time scaling, its bandwidth goes down by factor of 2. So this is one of the property that we have to use. Second thing is the Nyquist rate. How to calculate the Nyquist rate? So the Nyquist rate is given as 2 times of the bandwidth of the signal, or in general we say the 2 times of the maximum frequency content of the signal. Now we need to calculate what is the Nyquist rate of yt. We need to find out what is the bandwidth of yt. Okay. Now there is one more property we have to use. If you have any signal yt, which is xt into zt, and let's take the Fourier transform of this 2, so it will become yf equals to x of f convolution with z of f. Now from this convolution, if we try to find out what is the bandwidth of yf, so bandwidth of yf will be equal to bandwidth of x of f plus bandwidth of z of f. Okay, this is one of the property. So let's say bandwidth of this x of f is already given as a 10 kilohertz. Okay, and we need to find out what is the bandwidth of z of f to find out what is the bandwidth of y of f. So this is one of the property that we have to use. Now let's assume that this zt is this term, which is time scale version of the xt. Okay, so what will be the bandwidth of zt? So we will use this property. Whenever you do the time scaling by 2, bandwidth will go down by 2. We already know what is the bandwidth of xt, which is 10 kilohertz. So bandwidth of x1 plus t by 2 will be 5 kilohertz. So the bandwidth of z of f will be 5 kilohertz. So the bandwidth of y of f will be 15 kilohertz. Now in that case, the bandwidth, the Nyquist rate will be twice of bandwidth. So it will be 13 kilohertz. 30 kilohertz. So 2 into bandwidth is 15 kilohertz. So the Nyquist rate will be 30 kilohertz. So this will be the correct answer. Let's go to the next problem. Okay. Here, autocorrelation function is given of for the particular random process. We need to find out what is the power. So the power of a random process is given as expected value of x square t. And autocorrelation function is given as expected value of xt plus tau. Okay. If you put tau equal to 0 in this problem and in this expression, it will become expected value of x square t, which is same as power. Okay, so this is the formula that we have to use. The power is equals to autocorrelation value at tau equal to 0. So the value of autocorrelation at tau equal to 0 is 2, so that will be the power. So the answer will be 2 here. Now let's go to the next problem. Now, in this problem, it is based on the amplitude modulation. So there is an amplitude modulated signal which modulation index of 5 or zero point 0.5 or 50%. So mu is given as 0.5. Okay. If the carrier and one of the sideband are suppressed in the modulated signal, the percentage power saved is. So to understand this problem, we need to see what is exactly a carrier, what is the sidebands. So the AM signal is generally given as A plus MT cos omega CT. Okay, where A is some constant, MT is a message, and cos omega CT is a carrier. This can also be written as A cos omega CT plus MT cos omega CT. Okay, so this term is a carrier term, this term is a message term. So the power of this term will be the carrier power, the power of this term will be the message power. Okay, now if you have let's say message MT and its Fourier transform is m of f, and let's assume that m of f looks like this. Okay, now if you take this MT and multiply with cos omega CT, okay, so the Fourier transform of this term will be something like this. So this is the spectrum of this MT cos omega CT. Now in this spectrum, this portion and this portion, we call it as the upper sideband. Okay, and this portion and this portion, we call it as a lower sideband. Okay, so this is the upper sideband, this is the lower sideband. That's what it means by sidebands. Now this sideband contains the equal power. It means the lower sideband has same power as the upper sideband. Now let's use this mu now to calculate further. So eta, which is efficiency of the AM, will be given as mu square upon 2 plus mu square, which will be equal to 0.25 upon 2.25. Okay, which will be equal to 1 by 9. Okay, now eta is also given as message power upon total power, or message power upon carrier power plus message power. Total power is carrier power plus message power, which is equals to 1 by 9. Now if PM is x, then PT, which is PM plus PC, will be 9x. Okay, so from this we can calculate what is the carrier power. Carrier power will be 8 of x. Okay, so the message power is x and the carrier power is 8 of x. Now in the problem it is mentioned that we are removing or suppressing the carrier and one of the sideband. So if you remove the carrier, you will remove this at x power. If you remove the one of the sideband, So the upper sideband contain power which is equal to x by 2. Lower sideband contain the power which is also equal to x by 2. So let's say that we are removing the LSB. Okay, so we have removed this LSB, one of the sideband, and we have removed the carrier. So total power that we have removed is x by 2 plus 8x, which is equal to 17x by 2. So this is the total removed power. Now in terms of percentage, how much power we have saved? So that will be 17x by 2 upon total power was 9x. So that will come out, if you multiply it by 100, it will become percentage, and that will come out to be 94.4%. So the answer will be 94.4. Okay. Now let's go to the next slide. Okay. This is based on the channel capacity theorem as well as the pulse code modulation. So those two topics are combined into the single problem. So here speech signal which is band limited to this 4 kilohertz is sampled at the rate of 1.2 times of Nyquist rate. So we need to find out what will be the sampling rate. So first let's try to find out what is the Nyquist rate. What will be the Nyquist rate? So Nyquist rate will be twice of the bandwidth, and bandwidth is 4 kilohertz, so it will be 8 kilohertz. Now the sampling rate is 1.2 times of the Nyquist rate, so sampling rate will be 10 kilohertz, which is 1.25 into 8. So this is the sampling rate. Now after the sample, we are going to digitize it with the help of the quantizer. Okay, and now quantizer is assigning 8 bit to each of the samples. So what will be the data rate or bit rate? So the sampling rate is 10 kilohertz multiplied by each sample is assigned 8 bit. It means 80 kilobits per second we are generating. Okay, so this is the bit rate. Now this bit we have to transmit over the channel which has SNR equal to 26 dB. Now what is the channel capacity? C that is equal to C equal to B log 2 1 plus SNR. Okay, so this channel capacity should be equal to this to transmit the signal with minimal probability of error or a small probability of error. Now SNR is given, but it is in terms of dB. But in this formula, we use this SNR as a linear scale, so we need to convert it to the linear scale. So in linear scale, it will become 10 to the power 26 by 10, which is 398. So now let's put everything here and calculate the B. So C is 80 kilobits, which is 80 into 10 to the power 3 equal to B log 2 1 plus 398. Okay, if you calculate all this, you will get the B. Okay, so B will come out to be 9.26 kilohertz. Okay, so the answer will be 9.26. So in this problem, it has combined the sampling theorem, it has combined this PCM concept as well as the channel capacity theorem. Okay, now let's go to the next problem. Okay, this is based on the delta modulator, and the problem is based on this slope overload. So to avoid the slope overload, so let's assume that the delta is the step size. Ts is the sampling time, which is opposite of the fs, so delta into fs. This term should be equals to or greater than equal to rate of change of the message. Okay, so if this thing is satisfied, this slope overload will be avoided. Okay, so d by dt of mt. Now mt is a sinusoidal signal with 4 volt, and this is the frequency, so you can write it as a 4 sine 2 pi into 4 into 10 to the power 3t Okay, so delta fs is 32. It is given 32 kilohertz, 32 into 10 to the power 3. Now if you differentiate it, you will get 4 into 2 pi, oh wait, uh, into 4 into 10 to the power 3. This sign will become cos, and this is greater than equal to 2 pi into 4 into 10 to the power 3 t. Now this should be true for all the case, so we will take the case when this is maximum. Okay, so when this is maximum, this cos term will become 1. Okay, and then we need to just take this term. So in that case, del into 32 into 10 to the power 3 equals 2 pi into 16 into 10 to the power 3. Okay, so this 16 into 2 32 will cancel out this 32, 10 to the power 3 will cancel out this 3, 10 to the power 3 you will be left with pi. So del will be equal to pi, which is 3.14. So this answer will be 3.14. Now let's go to the next problem. Okay, this is based on the phase modulation. So the phase modulated signal is given as phase modulated signal is equals to 2 cos 2 pi 10 to the power 6t. So I am taking it from here. This is a carrier. So the phase modulated signal will have this carrier plus the message. So message is given something like this, kp into mt. So this is the message term. So message is in the phase, where kp is the phase deviation constant. It is given here. So we know this is the form of the phase modulated signal. Now we need to find out what is the maximum instantaneous frequency. Now this is the phase term. This complete thing is a phase term. Let's call it as a theta. Now the frequency is given, instantaneous frequency is given as 1 upon 2 pi d theta by dt. Okay, so if you calculate it, it will come out to be 10 to the power 6 plus kp upon 2 pi d by dt of mt. We are differentiating this complete term with respect to t and then divided by 2 pi. So after doing some calculation, I reached here. Now 10 to the power 6 plus kp is 2 upon, so this is the kp, I have replaced it with 2 divided by 2 pi. Now let's differentiate this message. Now what is the message here? So the message is a sinusoidal signal which has root mean square value of 4 and frequency 1 kilohertz. So the message mt is 4 root 2 sine 2 pi into 10 to the power 3t. Okay, I am writing it as a 4 root 2 because this is the RMS value. So peak value will be root 2 times of the RMS value. So now let's differentiate this message with respect to time. So we will get 4 root 2 cos 2 pi into 10 to the power 3t, and then there will be term 2 pi into 10 to the power 3. Okay, this 2 pi and this 2 pi will cancel out each other. Now if you calculate this complete thing, it will be somewhere around this much value. So this will be the answer. Okay, now let's go to the next problem. Okay, this is based on the superheterodyne receiver, and this is very easy problem. So we have a mixer. It's getting the LO signal and the received signal, or the signal we want to receive, which is at 600 kilohertz, and the LO is working at 1000 kilohertz. Okay, and then this is down converted signal. Now if you see it, let's say this is the frequency axis, and let's say in the frequency axis this is the LO and this is the message. Okay, so generally image will be somewhere here. We call it as an image because if you take this as a mirror, this will fall on here. That's why we call it as an image. Now the distance between these two is same as distance between these two. Okay, Now this one is at 1000, this one is at 600. Sorry, only 600. So the distance between these two is 400. So the distance between these two will also be 400. So this point will be 1400. So the image will be 1400 kilohertz. Okay. Okay, now next problem. Okay, this problem is based on the information theory and coding. So when in this problem, we need to find out the information gained knowing that the randomly selected girl student studies commerce. These are all the background. So we have so there is a school which has equal number of boys and girls. 75% of the students study science, 25% study commerce. Commerce students are two times more likely to be a boy than a science student. The amount of information gained in knowing that the randomly selected girl student study commerce. So the information is given as log 2 1 by p. So the information that is contained in a particular event will be equal to log 2 1 by p, where p is the probability of that particular event. So we need to find out this information. We need to find out what is the probability of that particular event, and that event is this one, this line. Okay, we need to find out what is the probability of this one. So let's assume that there are total 200 students. Okay, so there are 200 students. It means that 100 of them are boys and 100 of them are girls, and also 100 of sorry, there are 75% student science, so it means that 150 of them are science and 50 of them are commerce student. Okay, now one more information is given that commerce student are two times more likely to be a boy than a science student. So let's put some notation. Let's say CB denote the number of boy in the commerce, CG denote the number of girl in the commerce, SB denote the number of boy in the science, SG denote the number of girl in the science. Now the likelihood that the finding a boy in the commerce is two times of the likelihood of the boy in the science. Okay, this is the relationship given, and one more relationship is given that science student are three times of the commerce student from here. Okay, so CB equal to C 2 into SB upon this S will be 3C, the C will cancel out. So the number of boys in the commerce is 2 by 3 times of the number of boys in the science. Now the total number of boys is 100. So total number of boys is boys in the commerce, boys in the science is equals to 100. So that is, it will become SB plus 2 by 3 SB equals to 100. So if you solve this, you will get number of boys in the science, and that is equals to 60. Okay, so number of boys in the science is 60. So number of boys in the commerce will be 40. So number of the girl in the commerce will be 10. So CG will be 10. Okay, now what is the probability that we found if we select any commerce student? Okay, so here we need to find out what is the probability that if we select a girl student, she is studying a commerce, commerce subject. So we need to find out the probability that amount of information gained in knowing that randomly selected girl student This thing we need to find out. Okay, so the probability that out of all the girl, what is the percentage of the girl in the commerce section, that's what it means. So the total number of girl in the commerce is 10 and total number of girl is 100, so it will come out to be 0.1. Okay, so the probability that if we select the randomly girls student, she is studying a commerce, is zero point 0.1. Now let's put zero point 0.1 here, so it will belong to 10. Okay, if you solve this you will get 3.323. Okay, so that will be the answer here. Okay, now let's go to the next problem. Okay, again a PCM problem, pulse code modulation problem. So a message signal is given, it's a peak to peak value is 2 volt and the root mean square value is 0 0.1 volt, and this message signal is has a bandwidth of 5 kilohertz and it is sampled and fed to a pulse code modulator system that uses uniform quantizer. The PCM output is transmitted over a channel that can support maximum transmission rate of 50 kilobit per second. Now, assuming that the quantization error is uniformly distributed, the maximum signal to quantization noise ratio that can be obtained in the PCM system. Okay, so here we need to find out SNR at the last, which is signal power upon noise power. Okay, now signal power is very easy to find out because RMS value is already given. So the signal power is RMS value square. So the signal power will be 0.1 square, which is 0.01. Okay, now to calculate noise power, so noise power is given as del square by 12, where del is the step size of the quantizer, and that we need to find out. Okay, so del is given as, so the del can also be calculated from this, so range of message upon total number of level, quantizer level, so total number of level in the quantization. So range of message we already know is 2 volt, but we don't know what is the total level of quantizer. Okay, so let's find out what is the total level of quantizer. Okay, so here we are sampling it at the rate of 5 kilohertz. Sorry, the signal is bandwidth is 5 kilohertz and we are sampling it. So we will sample it at the rate of Nyquist rate. So the sampling rate will become twice of the bandwidth, which is 10 kilohertz. So this is the sampling rate. This is a 10 kilo samples per second we are getting. Now after the PCM output, so here the data rate is 50 kbps, the maximum data rate that can be transmitted, and this is a sampling rate. So the number of bits that can be assigned to each sample will be 5. Okay, so this is the number of samples per second. This is the bit rate per second. If you divide this with this, you'll get the number of bit assigned to per sample. So bits per sample will be 5 bits. Okay, so this is the 5-bit quantizer. Now if the quantizer is a 5-bit quantizer, number of level will be 2 to the power 5. So the del will be 2 upon 2 to the power 5, which is 1 by 60. Okay, so now we have everything. We have signal power, now we have del also, so we can calculate noise power. So noise power will be 1 by 16 square into 12. Now let's put it here. Signal power is 0.01 into 16 square into 12. If you solve this, you'll get somewhere around 32. So this will be the answer. Okay. Now let's go to the next slide. Okay, this is the last problem. So this problem is based on the minimum probability of error, or you can say maximum a posteriori. Okay, this is one of the theory which is based on how to minimize the probability of error. So to find out the threshold, we use this we use this method map. So let's see how to find it. So we have a noise. So let's say this is transmitter X, and before receiver we are adding some noise which is Gaussian noise. It is given in the question, and then it receives the receiver. Let's say received signal is R. So R is noise plus transmitted signal. Okay. Now this R can be n plus 2, or it can be n minus 2 based on what we are transmitting. If we are transmitting plus 2, it will be n plus 2. If we are transmitting minus 2, it will be n minus 2. So you can say R will be equal to n plus 2 if x is equals to 2, and R will be equal to n minus 2 if x is equals to minus 2. Okay. Now to find out what is the threshold, we use one formula. So what we use is that we have one symbol 0, probability of sending the symbol, and whatever we received, probability of sending 1, and whatever we received here. So just we have to equate this two. There is a derivation behind this. So if you open any textbook, they will there you will find this derivation. So if you make this constant that this is equals to this one, and then you will be able to find out what is the lambda, which is the threshold, optimum threshold. Okay. But in this problem, we need to find out what is this expression, and what is this expression. Okay. So when you are sending 0, we need to find out what is the PDF of received signal. Okay. So when you are sending 0, it means that you are sending minus 2 in terms of voltage, and you will receive n minus 2. Okay. So at the receiver, you will receive R equal to n minus 2. Now, since n is a random number, R will also be a random number. Only the thing is that it will get shifted by minus 2. Okay. Now n is a noise with Gaussian PDF. Now let's write its PDF expression. So it will be Pn where n is a noise, 1 upon under root 2 pi sigma square, where sigma square is the variance of the noise, minus x square, or let me write x minus mu square by 2 sigma square, where mu is the average of the noise. And since it is a Gaussian noise with zero mean, it is given in the problem itself, it is zero mean. It means that this mu value is 0. Okay, so this mu is 0 for the noise. But as soon as you add a minus 2 here, the mean will no longer be 0. It will shift by minus 2. So if you take this R, which is also a new random variable, its mean will not be equal to 0 but minus 2, given that we are transmitting minus 2. Okay, so if we are transmitting minus 2, then the mean value will be minus 2. So this R is also a random variable which is also a Gaussian, because this n is Gaussian, but its mean is minus 2. So we can write down what is the PDF of this, because this will be Gaussian noise with mean equal to minus 2. So you can write its PDF as 1 upon 2 pi sigma square exponential to the power x plus 2 square by 2 sigma square. There is a minus sign, yeah. So this is the PDF of this one. or let me write it lambda here instead of x, because now it is in terms of lambda. Okay, similarly you can calculate the PDF of this one, so that will come out to be 1 upon 2 pi sigma square exponential to the power minus lambda minus 2 square upon 2 sigma square. Okay, now we need to multiply it with p of 0, and this one we will multiply with p of 1 and equate them to find out what is the value of lambda. Okay, now p of 0 is given as p of 1 is given as 0.4, so p of 1 is given as 0.4, so the p of 0 will be 0.6. Okay, because we have only two event and total event, probability of total event will be 1, so the probability of 0 will be 0.6. Now let's put all this expression here. So p of 0 is 0.6, 1 upon under root 2 pi sigma square exponential to the power minus lambda plus 2 square upon 2 sigma square. This will be equal to zero point 0.4, which is p of 1 here, and then 1 upon 2 pi sigma square exponential to the power lambda minus 2 square upon 2 sigma square. Okay, this term and this term will get cancelled out. Now okay, okay, let me erase this portion. Okay, now this and this one got cancelled out. We are left with now 0.6 exponential to the power minus lambda plus 2 square upon 2 sigma square equal to 0.4 exponential to the power minus lambda minus 2 square upon 2 sigma square. Okay, now you can further write it as a 3 by 2 equal to exponential to the power. So what I'm doing here, this I'm dividing this by this, and let's take all this exponential to the power this side. So it will become 2 sigma square lambda plus 2 square minus lambda minus 2 square. Okay, so 3 by 2, let's take the log on both sides, so it will be log base e 3 by 2 equals to 2 sigma square. Let's expand this, lambda square 2 lambda plus 4 minus lambda square plus 2 lambda minus 4. So this and this one will get cancelled out. Now here variance is given zero point 0.4, so you have to replace the sigma square with 0.4 and just calculate. Now we have just only one variable left, which is lambda. Now if you calculate it, you'll get lambda equal to 0.04. Okay, so that will be the answer. So this will be 0.04. I think that's all for the communication system problem. So we have solved all the 11 problem based on that. So not all the problem were tough, only few of them I can say is tough, uh, and require slightly lengthy calculation, but rest of them were very easy.